Alright, welcome back guys. So today we're going to be practicing a basic incline block problem, and this is going to be practicing everything we've learned about forces up until this point. Alright, so here's the problem. So we have a ramp and we have a block on that ramp. Now we know the angle of inclination is 17.82 degrees, and we know the block is 50 kilograms. And we also know that gravity is essentially normal gravity on Earth, so 9.8 meters per second squared. Now we're told that this ramp is a frictionless surface, and we're asked to find the acceleration of the block down the ramp. Now most people might assume the acceleration of the block down the ramp would simply be the acceleration of gravity, 9.8 meters per second. And this isn't really true. So let's redraw this diagram. So we have two major forces at play here. We have gravity firstly. Now gravity does not act perpendicular to the ramp. Gravity is going to act straight down. So it's actually going to act at an angle to the ramp. Now the normal force, however, the ramp pushing back up on the block, is always going to be perpendicular to the surface. So that will be perpendicular to the ramp. Now the normal force is equal to this component of the force of gravity. So these two forces cancel out, and that's the reason that the block's not physically moving into the ramp or physically rising up off of the ramp. And now both of these forces, because they are perpendicular to moving down the ramp, they aren't going to affect the acceleration of the block down the ramp. Now they cancel out, so for our purposes, these forces essentially do not exist. So what we're concerned with here is this component of gravity. Now this component is the component that's perpendicular to the ramp, and this is the component of gravity pulling down on the block that's actually going to cause the block to accelerate down the ramp. Now normally you have to take into account friction acting in the opposite direction, but in this case, again, we're told it is a frictionless surface. So with this triangle right here, where we broke down gravity into its components, this angle right here is actually equal to the angle of inclination. So this is 17.82 degrees. Now, using this and using the force of gravity on the block calculated with Newton's second law, we can figure out this component right here that we're interested in. So we know Newton's second law is F net equals ma. Now we know the acceleration of gravity and we know the mass of the block, so we can find essentially the hypotenuse or the force of gravity, which will be equal to 50 kilograms times 9.8 meters per second squared. And now this essentially gives us a force of 490 newtons. Now this is not the component that is perpendicular to the ramp. This is simply the force of gravity before it's broken down, acting straight down on the block. So now we know this side is 490 newtons. Let me redraw this triangle. So now with some basic trig, we can figure out this component, which is the one that's perpendicular to the ramp. And that'll be 490 sine of 17.82 degrees. And when we work this out, we get 150 newtons. So the component of gravity that is actually causing the block to accelerate down the ramp is 150 newtons. However, that's the force of the acceleration. The question is asking for the acceleration of the block down the ramp itself. So now if we look back at Newton's second law, F net equals ma, we know the force that's causing the acceleration, or F net in this case, is 150 newtons. And this is equal to the mass of the block, which is 50 kilograms, times the acceleration. So if we divide 150 newtons by 50 kilograms, we learn that the acceleration of the block is 3 meters per second squared. So an acceleration of 9.8 meters per second due to gravity downward on this ramp will actually cause the block to accelerate 3 meters per second down the ramp if friction is neglected. And this is our final answer.